equation, that's right. But there is a better way to solve that. Here at the top, the velocity is 0, we have potential energy. And then here at the bottom, all we have is kinetic energy. So we can easily write conservation of energy for mass A and then solve the velocity before impact. That would be our first task. And once we have the velocity right before impact, then that would be an impact problem. And then we can go from there. So the first step would be conservation of energy. For ball A, for mass A, which means that potential energy plus kinetic energy of the first instant, we have the final potential energy and final kinetic energy. At instant 1, we don't have any kinetic energy. And then we don't have any potential energy when the ball gets down to the bottom. So potential energy is mgh, kinetic energy is half of mv squared. The mass is the same, so we are trying to find the velocity of A. So let's write the subindex A. So VA would be 2gh. And I know h is half of L, so if I replace h as half of L, it's simply GL. And the length L is given as 10 feet, and then I'm using the FPS system. So G would be 32.2 times 10, square root of that, so that would be 17.94. And the unit is feet per second. So conservation of energy, the energy is conserved. I don't have any friction. I don't have any other forces acting on ball A. The potential energy is changing to kinetic energy. So that's a classic example of conservation of energy. So I found the velocity at A right before impact. So what would be the next step? I see some of you are.
Could we use the coefficient of restitution to solve for VB?
Sure, we have to use coefficient of restitution, but that's not the only parameter that we have to use. That's we have an impact problem here. From here is an impact problem. For impact, you remember how many equations do we have in general? If I have an impact of object A, object B, let's say we have a velocity of A coming here, and after that we have velocity of B. I'm just going to assume both of them to be towards positive X. How many equations for an impact of two objects do we have? Two equations. Well, we have two equations in each direction. So we divided the direction from perpendicular line of action. We call this line of action. And then we call this perpendicular to the line of action. So for each case, we are going to have two equations. The equation that we have for line of action. Can you tell me what equation do we have for line of action?
Would you have a conservation of momentum for A and B?
Okay, very good. So that's one of our equations, conservation of momentum. We have to write conservation of momentum for both objects. because we want to get rid of all the forces that is happening around here. That would be our internal forces. So we can write conservation of momentum for both objects when we are looking at line of action. And the momentum is not conserved for single object, but for both of them, we can write conservation of momentum. So let's write our first equation, conservation of momentum for both objects, which means that MA VA1 plus MB VB1 equals MA VA2 plus MB VB2. So momentum is directional. So we write momentum for an axis, for a direction. We are writing a momentum equation for line of action, for the x direction. So if you look at the problem, B does not have any initial velocity. B is stationary when A is contacting B. But at the second instant, both of them are going to have a velocity. For now, because we are not going to deal with the direction, I just assume everything to be positive x. So I found the velocity at A here, 1794. And all the masses are the same because MA is the same as MB. So I can already simplify the equation. I can call VA1 equals VA2 plus VB2. And I know the value for VA1. I already found that value, 1794. So this is my first equation that I wrote for the line of action. As you can see, we have two unknowns. We have the two velocities after the contact. So to solve for these two unknowns, we need one more equation. What equation can we write?
The coefficient of restitution.
Coefficient of restitution. Very good. So the other equation that we need to write is the coefficient of restitution. So the second part would be 2. I write it the second equation. I have E. Coefficient of restitution is the ratio of a relative velocity after contact over before contact. So VB2 minus VA2 after contact, these two, I don't know any of those. Then VB1 minus VA1. So VB1, the initial velocity of B is 0. I have this value, I have E. The problem is telling me E is 0.6. And I have VA1. Here I have a negative value, and then here there's a negative in E, so I can get rid of the two negative here. And just write VB2 minus VA2 is 0.6 times my VA. So 0.6 times VA, which is 1794. It gives me 10.76. And the unit is foot per second. So I have two equations now. I call this my equation 2, VB2, VA2. The other equation that I have is VA plus VB. So two equations, two unknowns, and we can solve for the two unknowns. And these two equations are pretty simple because in one equation, VB is positive, in the other one, in one equation, VA is positive, in the other one is negative. So if we add the two together, VA cancels. But from 1 and 2, we find VB2. We can find VA2, but we are not interested to see what happens to VA after contact. We want to see what happens to B after contact. So that would be foot per second. So that's for the velocity after contact. So we wrote two equations for the line of action. So for any impact problem, regardless of how complicated it might sound, you need to remember first identify the line of action. What is the line of action? I have two equations for the line of action. And then we also have two equations for perpendicular to the line of action. For this problem, we didn't need to use them, but just to practice. Do you know what those equations are? Who can tell me the equations for perpendicular to the line of action? For impact problem, we have two equations also for perpendicular line as well.
Would it be conservation of momentum for A and B, but separately?
Very good. That's exactly what equation we are referring to. We can write conservation of momentum for each of them separately because the forces that are acting here are in line of action. So there is no any force in perpendicular to the line of action. So we can write conservation of momentum for each case. For this problem, we didn't need it. There is no component of velocity in perpendicular line of action. But if you need it, you can find it. So here the problem is not done. We have the velocity after contact. Now we have the velocity of B after contact. The problem is asking for how far this one is going. So we want to find H. The problem is actually asking for theta. So we want to find theta. But if we have H, we can find theta. According to the geometry, H would be L, the whole distance here. Let me clean up the image a little bit so we can see better what's going on here. So this is L. This distance would be L cosine theta. The difference between the two would be H. So H is actually L minus L cosine theta. So if we find H, we can find cosine theta. Theta is the unknown the problem is asking for. Now we have the velocity at B. We want to find how far or how high it goes. What is the approach that we need to use?
You use conservation of energy.
Conservation of energy, exactly. We use conservation of energy here. We are going to use conservation of energy over there. So same thing, conservation of energy. Let's write here, conserve. Of energy, we have V2 plus T2, condition 2, and I write it based on 2 and 3. You can still call it 1 and 2, really. Doesn't matter. For V2, is 0 is all kinetic, at the end is all potential, so you're not going to have any potential. So we have half of MB VB2 squared equals to MB GH. Again, the M's would go away. We need to find H. So that would be VB2 over 2G. After we plug in the value, we have the value for velocity at B. We have, of course, G. H would be 3.2. Now, after finding H, we said that H is L minus L cosine theta. The problem is asking for theta rather than H. So after this, it's not really dynamic, it's just geometry. So then theta would be cosine inverse of 1 minus H over L. Theta would be 47.2 degrees. So the angle here would be 47.2. So we wrote conservation of energy 2 times and then an impact problem. So it was 2 conservation of energy and 1 impact. Any question about this problem? So the problem was not actually, it didn't have any particular tricky point. As long as you follow the basic dynamic equations, you should be able to solve this problem easily. It had multiple components. In the exam that would be on Monday, because the exam time is short. It's not 1 hour and 30 minutes like previous exam, it's only 50 minutes. So I would break up the problems. So if I want to assign this problem, I'm going to give you the velocity before contact, and I will ask for the velocity after contact. So I will remove the first part and the last part. Or I would pick another portion of the problem. It should not affect your preparation for the exam. You still need to know everything about all the homework problems, but you don't need to be worried that you would run out of time. I would make sure that the time is reasonable with the given number of problems. If there is no question, we can move to the second problem.
What was the answer for the angle for that first one?
47.2.
Okay, thank you.
Sure. Problem 2, if the rod of negligible mass is subjected to a couple moment of 30 t squared and the engine of the car supplies a traction force of 15 t to the wheels, where t is in seconds, determine the speed of the car at the instant 5 seconds. The car starts from rest. The total mass of the car and rider is 150 kilogram. So by looking at the problem, can you tell me what approach do we need to take? We have the initial velocity is 0. You want to find a velocity after 5 seconds. Velocity at 5 seconds. And we have the force and a moment here. Does anybody have any suggestions? Can we write conservation of angular momentum? Let me see. Trevor? Can we write the conservation of angular momentum for this problem? I think you're muted for some reason. But if you're responding, I can't hear you.
Oh, sorry, I was muted.
Sure.
I think you can.
Okay. Anybody else? Do you agree or disagree with Trevor? Well, looking at the problem, we can't write conservation of angular momentum because the angular momentum is not conserved. We have this force is going to create a moment. We have a moment on our system. While we can write conservation of angular momentum, but we can still write the principle of angular momentum. So if you write principle of angular momentum, the principle of angular momentum is saying that the initial angular momentum plus the impulses that we are going to have on our system would be equal to the final angular momentum. So here, the initial angular momentum, because the velocity is 0, so we are not going to have any initial angular momentum. Now the impulses, the angular impulses, all the moments that are going to act on our system. We have a moment here. Also, we have a force. This force is going to create a moment. So we have two moment components. So if I want to write that, it would be from 0 to 5. The moment that I have is the actual moment that I don't need to do anything about it. I just write it. And I have the force. The force, if I want to change the force to moment, I have to multiply by the moment arm, which is 4. So I just write 4, 15 dt equals the final angular momentum, which is r m v2. I need to find, v to the final velocity. That's what the question is asking for. So if the r value would be 4, here would be 4 m, total m would be 150. So only I have one unknown, v2 would be 3.3 meter per second. So using the principle of angular momentum, we could solve the problem. And the problem becomes very simple. If you want to use other approaches, it would be very challenging. So here we had the initial velocity, we want to find the final velocity. But we have momentum acting on our system and also angular momentum. So we could write the conservation or principle of angular momentum and solve for the final velocity, which is 3.33 meter per second. So if these forces and moments act on our system, the velocity will increase from 0 to 3.33 in 5 seconds. Any question about this problem?
Nope.
Okay. Feel free to ask any questions that you might have.
I'm sorry, just one quick question
Sure.
about that. So it's not conservation of angular momentum. Why again?
Because conservation of angular momentum when we don't have any impulses. These are the impulses that we have. These are the angular impulses that we have in our system. This force is going to create an angular impulse for us. There is a force and there is a radius. So about this point, I call this point O. I have force F and I have moment M. These two are present. If these two were absent, then I could write conservation of angular momentum between initial and final.
Okay, thank you.
Sure. So let's move to the third problem. Looking at the problem, so the gear A on the drive shaft of the outboard motor has a radius of 0.5, gear B 1.2. So these are a typical example of bevel gears. Bevel gears change the direction of rotation. So the rotation comes here to this axis and goes over there. So you can transform motion between two perpendicular shafts. Does anybody know what would be an application of bevel gears? Have you seen bevel gears anywhere?
Yeah. In a differential on a car.
Very good. Yep, that's a perfect example for bevel gears. In a differential, we are transmitting the motion from the drive shaft to the wheels. So you can see this is the drive, and then the two wheels could be here. So we are transmitting motion from perpendicular to the two, and it's conical. So they are commonly used in future classes that you're going to learn more about these type of gear. But for now, we're just going to solve our dynamic problems. So gear A is 0.5 inch and gear B is 1.2. So gear A is the small one, which means that it rotates faster, and gear B is the bigger one, which means that it rotates slower but carries the larger torque. So moving from gear A to gear B, we are actually decreasing speed. And that's good to know. So at the end, when we find an answer, we can just visually inspect it to see is that what we expected to get or we did something wrong. So the question is asking for determine the angular velocity of the propeller after 0.75 seconds. So this propeller is connected to gear B. So whatever gear B is rotating, this propeller is going to rotate with the same velocity. If drive shaft rotates with an angular acceleration of alpha. So we have alpha for gear A. We want to find the angular velocity for gear B. At least that's the first part. And then calculate the radial component of acceleration at point P. I want to find AP and as well. So for this problem, we can write the gear ratio. That's true that we are dealing with bevel gears that are connected in a conical pattern, but the gear ratio is valid here as well. But before writing, we can either find omega A first based on alpha A, find omega A, and then write a gear ratio to find omega B. Or based on alpha A, we can find alpha B, and then find omega B. It's really both approaches is the same thing. So if you have alpha A, because alpha is given as function of time, and I find omega, I have to use the derivative format, so which means that alpha is d omega dt. That means that d omega would be alpha dt. Omega A, I don't have any initial angular velocity, so that makes it simpler, just omega A. From 0 to 0.75 would be 400 t cubed dt. So from here I find omega A, 31.64 radian per second. So I had alpha A, I found omega. I can write the indices here. Maybe it would make it easier. So alpha A, omega A. After I found omega A, then I need to write the gear ratio to find omega B. So I want to find omega B, omega A is inversely proportional to the radii. So that would be RA over RB, which means that the bigger gear is rotating slower. So omega B would be RA over RB, which is 0.5 over 1.2, 31.64. I'll find omega B to be 13.18 radian per second. So first I found omega A based on alpha A and then gear ratio. I found omega B. So that's the first part of the problem. The problem is also asking for acceleration at point P. But before we get into it, let's see if actually omega B is less than omega A. Yep, omega B is 13.18, omega A is 31.64. So gear A is rotating faster, and then through the transmission, here we are reducing the speed, but we are gaining torque. So the torque, the load carrying capacity increases. So we are sacrificing the speed for more torque power. And that's the case for most gears. Gears are usually, we call it reduction gears. We are reducing the speed and to increase the torque. Getting the speed is very easy. Getting the torque necessary for our application is challenging. That's why we usually go from small gear to big gears. The second part of the problem is asking for the radial component of acceleration at point P. So we said that acceleration has two components. One is tangential and then the other one is normal. The problem is asking for normal. So that's AN is R omega squared, and it's towards the center. So let me calculate that. I can perhaps calculate it here. So AP The radial component or the normal component is r omega squared. I have r is 2.2 inch, so I divided by 12 to get in feet, and then I found it 13.18. That would be 31.86 foot second squared. So I found the angular, not the angular, the acceleration, the normal component of acceleration, or radial component of the acceleration. Any question about this problem? So feel free to ask any question that you have. If there is any part that is, there is a missing link, every part that you're trying to figure out, that would be a good opportunity to ask. So gear ratio is valid when the two centers are fixed, if they're not moving. In planetary gears, if the center is also moving, then we have to write the gear ratio based on its center. So that's what you need to be careful. But if the two centers are not moving, these gears are not moving, they're just rotating, then we can write the gear ratio. And always remember, we have inverse ratio. Omega B, omega A is RA over RB, or the small one rotates faster than the other one. Okay, if there is no question, we can go to the problem 4. If bar AB has a constant angular velocity, omega 4 radian per second, determine the velocity of a slider block C at the instant shown. So by looking at a problem, we already know everything about B. I mean, this is a velocity problem, so the problem is not asking for acceleration, so it makes it simple. We want to find the velocity. We have the velocity at B. The velocity at B is perpendicular to our link AB, and we have omega AB. So we have everything about B. We want to find velocity at C. There are two approaches for velocity. One is just relative velocity. The other one is ICE, or instantaneous center of zero velocity. I would recommend you using both, practice with both, because depending on the problem, one is much easier than the other one. So if you know both methods, then by looking at the problem, if you see you're in trouble solving one problem with relative velocity, you can easily switch to the ICE method and solve it. So it's better to know both and be equipped with both approaches. But in the exam, you have the choice of choosing whatever you want, because it's multiple choice. I can't force you to use a specific method. As long as the final answer is correct, then you're good. So we're going to go ahead and solve this with relative velocity. So velocity at C, if I'm interested in finding the velocity at C here, is velocity at B plus the relative velocity, C with respect to B. So velocity at C, I need to write everything in a vector form. So velocity at C, I don't know the magnitude, but I know the direction is in I. If this one is rotating counterclockwise, this one is pushing velocity C in this direction. Even if the problem was complicated and you couldn't really tell which direction velocity C is moving, as long as we know it's I, it's really not important whether it's positive or negative. If we find a negative value, which means that the assumption that we had is incorrect. What we know is in I direction. That's the critical point. Then the velocity at B, we can either find it in a scalar form and by inspection find the two components, or by a vector form. So here, if this is velocity B, the magnitude of velocity is 4 multiplied by 0.15 meter. And the angle, this angle has to be 60 degrees, because this line is perpendicular to this, and this one is perpendicular to that. So that makes it 60. So velocity at B, I know the x component is positive. That would be the x component, and the y component would be negative. So that would be 0.15. That's our link dimension, times 4 is omega, and after that is just sine and cosine. So sine 60 will give me the I component, and for cosine 60 will give me the J component. So I have velocity at C, I have velocity at B. Now I need to write VCB. VC with respect to B is omega CB cross RC with respect to B. Omega CB is a 2D problem, so it's towards Z. Here I assume that it's counterclockwise to be positive. Then at the end, if I find a negative value, then I know that the direction that I assume is incorrect. Omega CBK times cross RCB. C with respect to B, which means that from B to C. So we want to find this vector. We have the dimension 200, we have the angle. So the y component would be positive and the x component would be negative. So just write this. I don't have room over there. Let me write it here. Negative 0.2 sine 30 I plus 0.2 cosine 30 J. So I wrote, if I look at my equations, I can see for VC, I don't know the magnitude of C, so that's one unknown that I have. VB, I know everything about it. VC with respect to B, I don't know omega. So I have two unknowns. It's a vector formulation, so I can solve for the two unknowns. For I, VC, I don't know magnitude of VC. Then the other I component that I have is for VB. 4 times 0.15 would be 0.6. Sine 60 would be a square root of 3/2. So 0.6 square root of 3/2. And also the VC with respect to B, here K times J will give me the I component. K cross J, the cross product itself gives me a negative value. So just that, write that negative value, and then omega CB cosine 30. So cosine 30 would be, let me clean up here a little bit so I have room to write. Square root of 3/2 omega CB. And I have the J component. Just gonna write here. I hope that you can, by now you should be able to find both components of I and J. Then I have 0.5 omega CB. So here from this for I have two unknowns. For J, I only have omega CB, so I can find omega CB. If I write it here, omega CB is -3 radian per second. So it's not clockwise. I got a negative value. Getting a negative value, which means that the assumption that I had originally is incorrect. And my link CB is rotating clockwise. Now that I have omega CB, I plug it into this equation, again, negative value, and I find VC is 1.04 meter per second. So I found omega CB and VC. Again, VC, which means that it's going through a positive X. I assume positive X. I got positive correct. I assume clockwise, counterclockwise. I got clockwise. Any question about this problem? So as an exercise, I want you to go and solve this problem using the ICE method. And to me, for this problem, it's easy to solve for ICE method. Sometimes it's more difficult. Again, if you learn both approaches, then that's going to help you significantly in exams and in real applications, that once you're stuck with one method, you can switch to the other one. I'm just going to briefly show you the ICE approach. So if you use the ICE, I need to draw two perpendicular lines. So I need to know two velocities for a link to find the ICE. I know the direction of velocity here at B is perpendicular here, and I know VC. So I know my two velocities. My next task is to draw a perpendicular line here to these two. So here would be my ICE location. So if I draw this here, that would be ICE. That would be velocity at B. That would be velocity at C. This distance is 0.2. I know from here to here, for sure it's 0.2. From here to ICE, I still don't know. But if I look at the angle, this is 30 degrees. This is 90, this is 60, this is 30, so this is 30. And this one is also 30. So it's an isosceles triangle. If this one is 0.2, this one is 0.2 as well. So I know the distance from ICE to point B. So I know velocity B is 0.15. 4 is 0.6 meter per second. This is velocity at B. Now you want to find out omega CB is velocity at B over O over B. Velocity at B over this distance. This distance is 0.2. So 0.6 over 0.2. So 0.6 over 0.2. 0.6 is the velocity. OB is 0.2. Omega would be 3 radian per second. So that's using ICE method. You get the same answer, 3 radian per second. And then you could find VC as well now that you have ICE and you have omega CB. Any question about this problem? One thing,
What was the velocity of C found to be?
velocity at C, 1.04 meter per second.
Okay, thank you.
Sure. One thing that I want you to pay attention is that the ICE is only for velocity. I can't tell you how many times I've seen exams, the students use the ICE, the instantaneous center of zero velocity, for acceleration problem. It has nothing to do with the acceleration. Don't use it for anything about acceleration, about the radial acceleration, about the normal acceleration. Sometimes ICE is located in the same point that you could use it for acceleration, but it's just random. We don't have instantaneous center of zero acceleration. So make sure whenever we are talking about acceleration, completely forget about ICE. Just use relative acceleration equation. For velocity, you have the choice of which one to use. So that's an important point to remember. For acceleration, don't use ICE for anything. So let's solve the last problem. This was your homework problem as well. So I'm just gonna go over it a little bit quicker as we going through our time. the slider block moves with a velocity of 3 foot per second. So we have the velocity at B and the acceleration of B. We want to find an acceleration, determine the acceleration of A at the instant shown. So acceleration has two components. So AA has the tangential component and has the radial component. The radial component, after we find a velocity at A, would be V squared over R, and this one would be R alpha. So alpha AB. So when we are interested in finding the acceleration at A, we need to find alpha AB. And also we need to find the velocity at A. So the problem is asking for acceleration, but we have to do the velocity as well, the velocity equation. So I'm just gonna go over the solution to be faster and show you over the solution. Okay, let's see here. We need to find omega AB. Again, this part is finding the velocity, even though the question is not asking for it, but for acceleration, we need the velocity and we need the omega. So that's the initial part of it. For the exam, these problems are usually long. So I will give you the velocity. I will give you the omega CB. So to find the velocity, either we can use ICE or we can use the relative velocity problem. Again, for this problem, it's very easy to use ICE. We have two directions. So we find ICE here. Now that I have ICE and I have the velocity, I have this distance, which is 2 cosine 60. This angle is 60. So 3 over 2 cosine 60 will give me 3 radian per second. Once I have the location of ICE and omega, I can write VA. RAC or A, omega AB, I can find the velocity at A. The velocity at A, that's all I need to find the radial or normal component of acceleration. I mean, these are the two terms I keep using it interchangeably, so you know they are the same thing. And we are talking about radial acceleration or normal acceleration. So the normal component is the velocity. We already found the velocity times the radius, which is here 1.5. This is the center of the curvature. Again, this is acceleration, so we are not gonna find the radius based on ICE. It's just based on the radius that our point A is rotating about. So this is important. This is 1.5 is our R here. Then we write the acceleration equation. AA has two components, N, which we already know, which are already found, and AT component, which we don't know and we haven't found it yet. Then AB, we know everything about AB. It's 4, it's linear, it has one component. It's not rotating about any curvature, it's just straight all the time. So it's 4I. AA over B is a relative acceleration. It has two components. It has the tangential component and the normal component. The normal component, we can find it because we know omega AB, we already found it. And we have RAB with a geometry, direction from B to A. So we have omega AB and also RAB. Alpha AB cross RAB, we don't know the value for alpha, so that's the other unknown. That's one unknown and then the other unknown. In vector format, we can handle two unknowns. So RAB is from B to A. So we have the dimension, we have the angle, we can find our R. Then AA with respect to B would be alpha cross R. AAB, it has the, let's go here. It has the radial component and also the tangential component. So we found the radial component already. So alpha AB cross RAB. Replacing it with I and J component, we find the two unknown. This was one of the unknown. And this is the other unknown based on our I and j component. Because we have one unknown 1175, we find one, and then we found 118 here. If you want to find a magnitude, so 18, 1175, we can find to be 2149. So we found the acceleration for point A. So I'm gonna post this solution in case I've gone fast and you have missed some parts. I will post this solution here, which is a cleaner version of what I solved, so you can have it and go through it. And also I will post the recording of this as well. And if you have any question, you can ask me. My other classes will begin soon. But you could either send me an email, you could schedule a Zoom meeting. We can address that. Any final thought or question before we go? Is everybody good?
Yep.
Jason, what did you say?
Yeah, I'm good.
Okay. So again, the exam is on Monday on Canvas. You need to be logged in, ready to start the test at 2:30, the regular class time, and it takes 15 minutes. It's multiple choice, and the answers I will try to make it far apart. So if it is 18.5, I'm not going to give one answer 18.5, the other 18.6. So that would be a rounding error. They would be far apart, so you could identify them. But it should not affect your preparation. Don't think that because it's multiple choices, it makes it easier. It might make it even more difficult, not easier. And don't try to guess what problem is going to be in the exam, what problem is not going to be in the exam. Don't try to narrow down the questions. You need to prepare for the exam the same way you do it for others. The additional set of questions that we have is the conceptual question that we have for that is similar to the discussion that I usually post. The problems that I post for discussions. Our conceptual questions are going to be like that. Again, it's going to be multiple choice, so you could choose an answer. Okay, let me know if you have any questions, and hope you do well in the exam.